You're listening to Electrician Live with your host, Paul Abernathy. Well, hey everybody, welcome to another episode of Electrician Live. My name is Paul Abernathy, your host as always, and welcome to the podcast. Of course, if you're also watching over on our video stream, it's available over on youtube.com/MasterDNEC. So make sure you go over and check it out if you can get the live stream. That was the alarm. So we are live. So again, you can listen to the podcast over on electricianlive.com exclusively, or you can listen to it through our podcast platforms that we have on Spreaker, Spotify, Deezer, iTunes Radio, Apple Podcasts, all the different podcast platforms. You can listen to it if you'd like to listen to the show. If you want to be able to see some of the video content or to interact on the actual session where we have people that come in and actually will chat with us, then feel free to join us as well, and we can answer any questions you might have on the topic, making sure it's germane to the topic that we're talking about today. So what is today's topic? I'm going to talk a little bit about meg testing and how it applies to conductors as well as different types of cable assemblies, and when meg testing can be reliable and when it's not really reliable. Now, there'll be some things that we discuss that, for example, some people may disagree with, but I'm going to ask you to take the concepts of what we talk about today and really use some common sense approach to whether or not you're going to have a usable application with meg testing. Now, everybody that I know has at one point, electricians-wise, at one point in their career done meg testing or has gotten a megometer and have put it through the paces, different manufacturers. We're not gearing in on any specific manufacturer. I have talked to many of the manufacturers, and again, to me, some of the information that I get from them is a bit problematic because of the nature of the meg testing and what gets done with meg testers. A lot of the manufacturers I talk with, we'll talk about two different concepts when it comes to meg testing. From them, a lot of them say, the meg testers were never really designed to test conductors or cable assemblies that weren't medium voltage, that had a certain type of construction to make it conducive for meg testers to work properly. So we'll kind of go into those different concepts tonight on this show. And we'll try to convey it in a way, and we'll even look at a couple documents as well that might be able to convey some of that information that we need to know when it comes to meg testing. Now, I went through school in my program, in my training with testers, and back when I was in vocational school, we're all taught to do this. We're all taught to measure from A to B, B to C, if there's an A, B, to C, obviously, three-phase. A to B, B to C, A to C, all to ground, and look for these readings. Now, there's different types of tests you can do, and I'm going to make a recommendation today of the best tests that you would need to do if you're going to do meg testing. But let's kind of back up a little bit and talk about the concept of from a manufacturer's position. Okay, and I have the ability to talk from a manufacturer's position because I work for a manufacturer of wire and cable as well. So let's talk about what happens to wire and cable in a facility during construction, in case you didn't know. So typically in a wire and cable manufacturing facility, so we're going to talk about it from its creation to what the electrician would do on site and what to expect to get. So from a manufacturer's standpoint, if you have what's called, there's thermoplastic and thermoset insulation. So THHN, THWN-2, that's a thermoplastic, okay? And a thermoset is a material that would be like XHHW-2, RHH, RHW-2. Again, so the big difference between thermoplastic and thermoset is thermoplastics like THHN, that will melt, okay? So you have to be very conscious of where you use it, ambient temperatures and all these type of things. Even though both are rated 90 degrees C, it will melt. Whereas thermoset, which is like cross-linked polyethylene XHHW-2, that doesn't melt. That will crystallize to a point and then break down, but it will not melt. So manufacturers can't take that material and reuse it, whereas thermoplastic they could reuse. Okay, so let's get to the testing. Prior to you even getting the wire, or cable. It has to go through various tests with the manufacturer. Now, since we're talking meg testing, we'll talk about the application of the individual insulated conductors, like XHHW-2, because typically you get a choice within your UL standard. I can dunk tank test my wire, or I can do a spark test. Typically for the thermoplastic, most, not all, manufacturers will spark test their thermoplastic, which means it runs it through these beads. They look like little BBs. And what it's done, if there's any damage to the insulation, it will create an arc from the conductive copper or aluminum in the middle to these beads, creates an arc, sends it to the system, and kicks that wire off. And again, it just kicks it offline and recycles it, and you keep on going if there's damage. A very high complex test that can range anywhere from 3,000 volts up to 15,000 volts gets pumped into these beads, and this is what you end up having most of your thermoplastic wire run through. And so again, it's a very high level test, but the standard allows you to do two different ways. Now, the other way would be to dunk it. And so most manufacturers, not all, most manufacturers will spark test their thermoplastic, but they will dunk test their thermoset. So what they do is they'll take the reel, they'll take it over to a dunk tank. Usually that dunk tank, it's a big bathtub, is really contaminated anyway. Because, you know, water is, at purest state, water is an insulator, but of course it's got so many chemicals and so much crap in it that it becomes conductive. So what we do is they will take it and they will dunk it, and you will have two leads. The two ends of the reel, of the conductor that's on the reel, will sit above the water. But the flange, which is the outside perimeters of the drum, will actually go underwater. And so what happens is they'll connect the meg tester to it, okay, megometer. And so what they're doing is they'll have one lead goes to one end of the wire, okay, but the other lead will stay unconnected. What they'll do is we'll put a rod down in the water so that the other lead of the meg tester can connect to the rod. My copper rod stuck down in the water. So when you get a meg tester, you're going to have a choice of voltages. Now, the test standard that manufacturers utilize is either 500 volts or 1,000 volts. They have the choice. Obviously, the more voltage being pressure, you put more pressure through, it puts more stress on the insulation. But the standard only requires it to be 500 volts. So, for example, our company uses 1,000 volts, but other manufacturers might use 500 volts, and that's perfectly fine. But what it does, it's a perfect condition. Means that it pumps it into the wire. The insulation is underwater, and if there's any damage to that insulation, any weak spots, again, cumulative of the total surface area, then what will happen is that voltage will induce a leakage amount of specific current through the water, and it will be picked up by that probe up into the megometer. So you see here, these are the basic concepts. I have to have a return path. So the only way megometers work is to be able to pump out, put the voltage in, and be able to take a reading that comes back, right? So under that concept, anything that passes in a dunk tank from a manufacturer is going to have a label slapped on it that says that it passed. Then it gets shipped out to the job site. Now, you have to be very careful how you move the product from job site to work site. So you could have a truck that pulls up on the job site, but you have the work location, which is down somewhere else inside of the facility. So how you get it from point A to point B is going to play a critical role, because in my experience, I see a lot of people pick them up with forklifts and other things that will damage the insulation. Now, the interesting thing about damaging conductors insulation is that you usually won't damage it with the outer perimeter. The forks, if they hit it, will actually slide between the top layer and actually damage the conductors that are underneath it. And you won't know this until you start pulling it, okay? So it's real important how you position it and how you really take care when you're maneuvering this wire on this reel. The bigger the reel, the bigger the issues, the more the weight, right? Okay. So the next thing that people ask before we even get to testing is, do the manufacturers perform a test? Does the values that they do in the test condition going to be exactly the same as you could replicate out in the field? And the answer to that is absolutely not. It could never happen. One is because they're not going to dunk it. Two, we have a pure conductive medium that we're putting the reel in as a manufacturer, but in the real world, out in the field, There's air involved. There's field contamination involved. There's humidity that's involved, okay? There's capacitance or mutual capacitance when you're testing one conductor and then you jump to the next conductor. They will transmit a capacitance from one conductor to the other. We're so busy discharging the conductor we're testing, we don't think about the induced charge that could be on the conductor that we're now going to test. So there's so many things to think about, okay? So you get on the job site, you move it to the work site, you get it set up, and you pull your wire. Obviously, you need to have clean raceways. The raceways need to be cleaned and bushings put on where necessary with 4 gauge and larger. Everything needs to be done right. Your setup needs to be right. So now you've installed your wire. Okay, your wire's now in the actual raceway, and you're called in to do a MEG test. So traditionally through school, we're taught to do, again, whether it's 500 volts or 1,000 volts, and many people refer to a document called the Nita standard. Now, the Nita standard comes in 3 flavors, but the one that we deal with the most is the maintenance standard and the acceptance standard for new installations. Now, that sets a threshold of any test that would be 100 megohms or greater is an acceptable test. What they don't tell you is that is a voluntary document. That is not a mandatory document. And I see this being used all over the country as the benchmark for an installation. I will have you know that there is values can be well below 100 megohms and still be an acceptable conductor. Okay, and we'll get into that. So let's go by the benchmark. Let's say that the Nita standard is 100. Now, there's 2 different standards. Remember, I said it was 3, but the 2 that we're dealing with is the acceptance standard and the maintenance standard. Okay, so the maintenance standard is one that you would use if you're doing long-term observation, and I usually recommend facilities to do testing annually, especially in very critical or operational facilities that like the data centers, the Googles or whatnot, are all these places where they need to make sure they optimize their uptime. Now, they might have to shut down, obviously, to do this test, because to do a proper test, you need to take it off the terminals, okay? All of that stuff has impedance. All that stuff can affect your test. So it has to be a all-off type of test when you're doing a MEG test, okay? But you should have a procedure where you can do this annually, all right? That's where you would use the maintenance standard. Now, the initial acceptance standard is where you get it on site. Now, here's what I recommend. I'm just going to say this. You should check your wire or your cable assembly before you even install it. If you're going to accept it from the manufacturer and you know that you moved it from point A to point B and you did not damage it, it's one thing. But forklifts or improper handling can damage it very quickly, okay? The insulation on these conductors are put in a raceway for a reason, right? Okay, I'm going to talk about a bunch of stuff tonight, so hang on with me now. So now I'm putting it in a raceway. And before I even did that, I want to test it. Now, one of the most basic tests that I tell people to do is a simple continuity test. And I do this with all the wires. I used to have long leads, and what I would do is every reel, I'm testing continuity, making sure everything's okay from end to end of the reel, provided I can get to the ends. Okay. If it's a cable assembly, then I would go to each end and I might connect the black to red or whatever and test continuity through those. And I test each for continuity, okay, for those type of scenarios. I also, even though it's very rare, but even like an MC cable, I might test something where I test individual conductors' continuity to the armor. Now, we'll talk about that test in a little bit later because, again, that polymeric wrap on an MC makes it pretty hard to get a MEG reading. So you see where I'm leading up to, but we'll just kind of take it one piece at a time. All right, so in this case, my conductors are in the raceway now. Everything checked out. Everything was fine. You don't have a tank. You can't do dunk tests on sites, and most people don't have it set up. And you would never expect to get the values that a manufacturer can get. It's a perfect environment. It's set up for testing. You're in the field. So now you put all these conductors, and we're taught in school that we're going to set that Megohm meter up, and we're going to test A to B, B to C, A to C, all to ground, and we're going to test each one, and we're going to take a reading. Now, you might get a reading. Now, this is something that people always question. I want to explain. you might get 250 mega ohms. You might even get a giga ohm on the first reading. Okay? So your A leg to ground. Perfect. A leg to the perfect reading. You might get a B leg, another giga ohm. Perfect. Now you might get to C leg. And now the thing's only 75 mega ohms. And people freak out. They expect to get the same readings on all of the conductors as if they're all made at the same time. They're all made with the same componentry chemicals. You have to remember that the colors and the amounts of material that goes in each one of these can slightly be different. Okay? And so things like that can change it. Also, you could have one conductor that's sitting lower in the raceway that's flooded and has more moisture in it. Okay? You could have damaged that one during the install. But I'm telling you right now, we're going to talk about meg levels that I believe the Nita standard is only a starting point. You should always contact the manufacturer because they know their wiring cable better than anybody. Okay? You don't immediately just start ripping stuff out. Okay? Most manufacturers are going to leave you hanging if you do that. They're going to say, you didn't get us involved? How do we know you didn't damage it? We don't know that because we wouldn't ship it out if it didn't pass a test. Why? Because the facilities are checked and they have visits by, if you're being inspected by OSHA, not OSHA, excuse me, UL, the NERDLs, then they're going to come multiple times a month and check your facility. So, and you're going to have samples that are pulled and tested. So again, nobody wants to lose the ability to make their wire. So they're going to follow rules. Okay. Now, if you're believing some conspiracy theorism and then whatever, but I'm telling you, I work there. They take this stuff very seriously. Things can happen. We get it. But again, for the most part, there's a serious checks and balance going on. So, okay. So you've tested your wire and you get one that's low. And you're thinking, well, that's the reason it's low is because the insulation value is so low. It means there's a lot of return current is coming back on this conductor's insulation because it's leaking. And you're getting such a number that's not high. There's not enough insulation resistance in there. And you immediately think it's bad. And you're like, I got to pull it out. All right, so there's a document out there, and I'm widely known for it, where we call it the 2 to 99 rule. And that is once you get below 100 mega ohms, once you get down to about 20 mega ohms to 25 mega ohms, anything below that, it's time to investigate. But anything that's 20 to 25 mega ohms all the way up to the 100 mega ohms, again, doesn't mean it's bad. It means you look at the condition, but it doesn't mean it's bad. Okay? So it just means something it could be moisture, humidity, it could be capacitance coming from mutual conductors. Because look, when you do a meg test, again, you're putting a certain amount of voltage in. And whether it is 500 volts or 1,000 volts, which is typically what you're going to recommend for a meg test. We're not talking high pot test, high potential test. We're talking a meg test, non-destructive. High pot tests can be destructive. Okay, meg tests are not destructive. So you're putting this in here, and what you're trying to do is test this insulation. And so if I get a giga ohm on one, and I get a giga ohm on the second one, and the third one happens to be low, immediately in your mind, you think that that one should be giga ohms as well. And you have to remember, it could be the way it's positioned in the raceway, could be humidity, could be the conductor's insulation. If it was just made, it could be still curing. It's kind of rare, but it could be. There's other conditions that could be in play. Okay, so you're testing everything, take your readings. Now look, there's different types of tests. And again, some of them are not as good as others. So I'm going to talk about the different tests, and I'm going to tell you the ones that I recommend. Okay, the very first test is the test that most people do. And it's simply a 60-second test. We call that a spot test. That is the worst test to do. Okay, that is simply a spot test. It is, 60 seconds. By the time the conductor reaches up to its peak and you have its initial charging and its capacitance and everything that gets up in there, then you're looking for it. But by the time you get to that reading, that's not the best test. Now, the next thing you would do would be basically what's called a time resistance test. And the time resistance test is better because you can do up to 3 tests in one time resistance test. What this means is, okay, so if you want to do a spot test, that's fine. It gives you a short snapshot. The best test to do while you're doing this is to do a 10-minute test. So you're going to take a reading at 1 minute. You're going to take a reading with me. You're going to take a reading at 1 minute. Okay. Then you're going to take a reading at, take a reading. The first one I want you to take at 30 seconds. I want you to take one at 1 minute. Then I want you to take one at 10 minutes. Okay. So what are we going to do with these readings? Okay. Now, the first thing I want to look at, if I'm thinking about what's called the time resistance test, what I want to look at is before I start doing any ratios, which is a dielectric ratio test or a polarization index, the first thing I want to look at is that curve. What I want to see is over that period of time, once it started its curve over that time, did it ever drop below its 60-second value? So if it got to a certain at 60 seconds, for the next 9 minutes, did it consistently go up? Did it level out? Or did it drop below its peak at its 60 seconds? And that gives me a snapshot of the overall time. This allows me to get beyond capacitance. This allows me to get total absorption. And now I can actually see where my values are. Now, if it gets to 60 seconds and then for that 10 minutes, it starts to drop down or edge down, then we have something going on. That insulation is having a problem or something is contributing to it, whether it's moisture, humidity, or flooded race, something's going on, okay? Now, I'm giving you the basic steps, but then I'm going to get into some of the fallacies. So hang with me here. Next is while I'm doing that 10-minute test, I am going to make sure that I take a reading at 30 seconds before it gets to that 1 minute. Then I take that 1 minute, and then I'm going to go on and take the 10-minute reading, okay? So I've got all these numbers that I'm going to deal with. So the time resistance over time is the one I'm looking at the curve. I'm looking at the values. You can plot the curve, but I'm looking at what the numbers were at the point where it got to 1 minute and the point that it got to, since you're also going to take one at 5 minutes, and then I got the 10-minute. So I'm looking at that value, whether it's dropping, maintaining, or rising slowly. If it's constantly rising beyond its 1 minute test value, then that insulation is holding its own. It doesn't necessarily mean it is bad, okay? All right, now, so of the tests, the best test to do is a polarization index test. Now, you can also do a dielectric absorption test, which is a 60-30, which means I take a value at 30 seconds and I take a value at 60 seconds. In fact, for those that are watching on the video or over on our stream, I'll kind of take you over, if I can get off this here and take you over to an examples here. So again, if you're not on the video stream, you can't see this, but this is an example of the spot test where you're doing it at 60 seconds and you see an increased rise, okay? And then, of course, you have, like I said, the time test, which, as you can see over time, over the 10 minutes, you actually are looking for a constant rise, okay? So we're taking those values and taking those, okay? And I like to do a 5 minute, I like to do a 1 minute, and I like to take a 10-minute value, okay? A little more work, but a little more gives you a better picture. So as you can see here in a picture, those that are watching, you have another test that I'm telling you is the 60-second and 30-second. So watch the value at 60 and then take the value at 1 minute. Now, this is better than the spot test, which is just a 60-second alone 1 minute test, because you don't get the real picture of the rise, okay? And you get past what we call that capacitive point, and it starts to go up. So spot testing at 60 without any other observation is not my recommendation. Do what you want. But if you're going to do this, I want you to do a 30 and 60 second or 30 second and 1 minute, and that would be a dielectric test. Okay, so that's a dielectric absorption test. And what you're going to do is you're literally going to take that 60-second value and you're going to divide it into the 30-second value. And that's going to give you a ratio. Now, if your ratio falls 1.0 or greater, when you're dealing with wire and cable, not a problem, okay? Now, if it falls below 1.0, then it just means further evaluation. It means that immediately we're going to jump to the 10 and 1. Since you're already taking those values anyway, we're going to jump to that. And if you do a 10 and 1, means I take the value that I got at the 60 seconds, and then I take the value I got at the 10 seconds, and I divide the 10 into 1, okay? That's going to give me what's called a polarization index. And again, if it's 1.0 or greater for wire and cable, then I'm telling you it's probably okay. Then you would just consult with your manufacturer. So ideally, we'd like to see 2 or greater in the polarization index, and we'd like to see at least 1.4 or greater in the 30 to 60 second absorption test. That does not mean that 1.0 is bad when it comes to wire and cable. Now, that brings me to this. So I've kind of told you all the tests. We recommend the 10 and 1, but I would prefer you to do a test. Take a reading at 1 minute, take a reading at 30 seconds, 1 minute, 5 minutes, and 10 minutes. So basically, you're just doing a 10-minute test. That's the best. Dedicate 10 minutes to this test, okay? Don't be in such a hurry. That way, you've got a bunch of values that we can use in order to look at the ratios, polarization index, the long-term time curve or time resistance, okay? And you can even do that look at the 60-second and give you a spot. But what we're doing is looking at the overall picture. That's what I recommend. Remember, you're doing this once, hopefully, and to this detail that you take the time to do it, okay? All right, so now let's talk about the validity of these readings anyway, okay? So we'll come back to me, and we'll talk about the validity of this. Now, the validity of a test. With all these readings alone, okay? With all these readings alone, you've got to make sure that you have the ability for the Megohm meter to work properly, okay? Now, what do we mean work properly? Remember that little thing that we talked about at the beginning about the dunk tank that gets done for thermoplastics and cross-linked polyethylenes? It can be done for thermoplastic, but typically it's not. So remember that concept? The dunk tank. There's a reason there's a dunk tank test that's in the UL standards as an option. One is because you pump voltage into the conductor. Weakened insulation allows this differences of potential to cause a certain amount of current to transfer into the moisture or the water that's contaminated. It comes back to the probe and it gets measured on the megometer. Okay? So again, it's a process. It's got to go out. It's got to come back. Okay. When it comes to conductors, I know we're all used to seeing all these numbers, and we love the higher the better. But think about this for a second. If I've got a PVC raceway, I've got insulated conductors, I've got no bare equipment ground in there, everything is insulated. Everything. What am I connecting my leads to in a MEG test? A to B? They're both insulated. So that means I would have to have mutual damage or mutually weak insulation on both of these conductors in order to get a valid reading. Now, I'm going to get a reading, and it could be a high reading, okay? And that's great. It makes you feel good, makes you feel happy. You install it, you say, hey, it's above 100 megohms, the Nita standard, whatever, I'm good. Makes you feel good. But now you go to test the next one. And assuming that your equipment discharges any capacitance get placed, it will in that conductor. But you have a conductor that's next to it, and it could be mutually charged. And if that's not discharged before your test, you're now going to click onto it. Now, the worst case scenario is now you're charging 2 conductors, and you've got that third one that's being ready to test, and it's been subject to 2 other conductors that have voltage put in it, current leakage, if there was any. So now it becomes capacitive. Do you discharge each one of your conductors before your test? I hope you do. Do Megohm meters have a self-discharging feature in? Most do, and hopefully you utilize it properly, okay? It does discharge each conductor after use, again, because you don't want to have a touch potential there. But what about the conductors that are near it, that don't get connected to the system yet? Okay, so things to think about. Now, you could be testing the first 2 and everything goes great. But remember something. The raceway was non-metallic. The conductors were insulated. How are you really going to rely on this meter to function properly? Where's the return path? Now, where they become very valuable is if I believe there's damage to my conductors. Then I've got exposed material at a damaged location, and that's where it becomes very reliable. In order to be able to get a reading between two, where I notice some damage to a raceway, then again, I would recommend somebody, or damage to a cable, I'd recommend they do meg testing because, again, inside it could have damaged the insulation, and that's something that you can test, okay? So that's a viable use for that. But if everything is insulated and the raceway is non-metallic, do you really expect to get reliable readings from two insulated conductors that are running parallel with each other? Probably not, okay? So things to think about. Now, in the most perfect world, I have a rigid or intermediate or a EMT tubing, and I've got insulated conductors. Now I have a viable way of getting a return path because I can go to the actual metal raceway. And so I put this into the conductors. If there's weakened insulation or a problem, then I've got a potential return path on a conductive medium, okay? That's your best case scenario, right? So there's a benefit. Now that means also, while people don't do this, but when they pull equipment grounds in a raceway, nothing says, except for hospitals, when you're dealing with 517.13 A and B and whatnot, where you have to have an insulated ground, you could have, okay, a bare in a raceway. It does not have to be insulated, and you might increase your chances of getting some kind of reading in a non-metallic raceway with insulated conductors and a bare equipment ground. Nothing says that it can't be bare. Most people will insulate it, okay? So that's it. Now, so as long as you have a return path, you have a higher reliability rate. Now let's talk about MC cables. Let's talk about AC cables. You can, so at a facility, when we make a MC cable, we test it at high pod, because what we're doing is we realize that I cannot test a meg test very easily from the conductors to the armor. Why? Because the conductors are wrapped in a polymeric material. And I can tell you right now, polymeric material that we use to wrap those products in 600 volts or even 1,000 volts is not going to blow an arc through that polymeric material to get to the armor. I know personally because I've done it. In fact, I put 20,000 volts through it and it wouldn't bridge over the polymeric material. So what we're testing is making sure that it's not damaged in there, nothing has pinched the conductors. Then you get accurate readings from conductor to conductor because we're looking to see if there's a breach between conductors, if there's damage to the insulation, okay? That's what we're doing. When you get it out in the field, it's very hard for you to meg test MC cable because of the polymeric material. Even things like smart grounds or products that have the paper in it, like AC, it is very hard for you to be able to get that reading in there, okay? So even the smart ground type products where you have the bare aluminum grounding / bonding conductor, it's on the outside of the polymeric material. So that doesn't help you either, okay? So again, it's hard to meg test MC products, AC products, things like that. Now, if you have mutual damage between conductors, then yes, that might work. But if they're perfectly insulated conductors, it's really hard. The next thing that people ask me is they say, well, what about when I'm meg testing when I throw USC-2 conductors in a trench? And I go, how are you testing it? They go, well, we're testing a conductor, but then we stick a probe in the earth and we're doing a return through the earth. If you can't do that in the code because the earth has too high of resistance, you're not going to get accurate readings through the earth if that's how you're trying to test it. It's not going to work. And if you're putting them in the ground and you're testing conductor to conductor and they're both insulated, what readings are you trying to get? Now, you're going to get a reading because I would expect it to be high resistance. So you say to yourself, what happens when I get a low value? Something's got to be wrong. No, it could be a lot of things. It could be contamination. It could be moisture. It could be water that's being retained inside of the interstices of the actual conductor, which in itself isn't bad. It's not going to cause a problem. But it gets in there, whether from the manufacturing process or where you stored your wire. But at the end of the day, those things can cause readings to change. Again, you also have mutual capacitance. If you discharge the conductor you're testing, but you don't think about the conductor that's right next to it, and you immediately jump to test it, and then you jump to the next one, then you could be having capacitive issues that get coupled up on the insulation, and that could affect your readings, okay? Now, I'm not here to say that you get low meg readings. It doesn't mean you have bad wire. you could have bad wire, but it could have been damaged during install. And what you're getting is mutual damage between mutual parallel conductors, and that's what you're reading. The biggest concern to me when I test the system is to make sure that if I have a black and a white on each end and they're not touching, one of the first things I do is put a continuity tester on the black and the red and hope that it don't ring. Because if it rings, that tells me that somewhere in that run, there's been damage, and now I have a black and a red touching. And I do a lot of continuity testing amongst different conductors when I'm doing that test. I don't want anything to ring. If I have metal raceways, I test the black to the metal raceway. I don't want to hear anything ringing, okay? So that tells me, again, whether or not I have some type of damage to a conductor and it's becoming in contact with the armor. Maybe it's flooded, you've got contaminated water, and it's making that bridge. Those are the type of tests that I do that are more reliable. What I don't want you to do is just because a conductor has 100 gigaohms and another one might have 50 megaohms, that you immediately say that that's a failure, it's going to break up, it's going to blow up. Now let's pull that 50 megaohms out. That's not the approach. Contact your cable and wire manufacturer because they will be able to talk you through it. Again, there was this old adage that it was accepted to have 1 megaohm per 1,000 volts. Okay, so at the end of the day, that was what the old electricians used to utilize. And again, they were happy when they've got 2 and 3 and 4 and 5 megaohms for a conductor. Now we're conditioned to think that we have to have 100 megaohms. Now I know that engineering standards, the engineers will put Nita standard 100 megaohms on there. But remember, in that Nita standard, it also says to consult the manufacturer because that's just a recommendation. Now let's talk about that standard, okay? Let's talk about it for a little bit. In that standard, that is typically designed for use with medium voltage type of products. Now, the people that I talk to, the Megohm tester, Megohm meters, the meg meters, they have told me that their products weren't originally that designed towards low voltage wiring. It was really designed for transformers with a separator or motors with the winding separations, appliances that could cause a failure between the insulation to the metal housings. Those type of tests was really what they were designed for. Now, they work really well. Meg meters work really well on medium voltage. They work really well on high voltage. Now, medium voltage, you have a center core, you have a dielectric material separating it, and then you usually have a braided or singular helical outer set of conductors. And that is your guard. And in many cases, for utility, that can actually be your grounded neutral, and in the middle is your ungrounded. Now, because of that, you can get a reliable reading on one of those type of cables because you would simply connect to the outer perimeter armor or the outer braid that's just on the outside of the dielectric medium that separates the inner conductive portion. And if that insulation is weak, you can get a reading on it. And it will tell you how much absorbs to it because there's 2 paths that are mutual, okay? They're mutual. They're in the same cable. So the chances of getting a reading that's acceptable is good. Perfect for medium voltage. Perfect for high voltage that gives you that return path. But individual insulated conductors, it's very hard to do. If it's in a metal raceway, you just increase your chances. If it's all PVC and everything's insulated, you're going with numbers just to make you feel warm and fuzzy. Okay, now, with that said, let's shift gears to what's called the maintenance standard for Nita. Now, say everything is PVC, and let's say you get these readings. These are predictable readings based on the conditions that it's being placed in. You could mark those down, and you use those values as your measure point for your next test, which might be 6 months from now, might be a year from now, however your test is, and you plot it out. So then those initial readings that you get can be beneficial to plot a curve with potential breakdown of conductors or cables after installation. So you could have a position where you had something that was 100 megaohms, and then 6 months from now, it drops down to 12 megaohms. And then you're going to say, well, I'm not ready to yank it. It could be moisture, contamination. I'm going to give it another 6 months, and you plot it. And you might see that it goes back up. Maybe there's moisture in there on your initial test, and now over time, when you have current flowing, you're going to have heat, mutual heat, then some of that moisture is going to evaporate out or going to dry up. And so once that happens, you'll slowly see your meg values getting better. So you use that as an ongoing monitoring. That's what you want to do with that. Okay, so that is. Now, ironically, both of them say 100 megohms as their threshold, but remember, the Nita is a voluntary standard. It's not an enforceable standard, okay? It is just a recommendation that engineers will latch on to, but the reality is they do not know wiring cable and the use of those products like a manufacturer would. So whoever the manufacturer is, always reach out to them and say, this is what I've got. Tell them what you've done, and I do this all the time. And I can tell you without fail, usually we can nail it down to what's going on. And knock on wood, we haven't had any fail yet, even when their megohm values were down as low as 20 megohms, because we looked at the overall picture and we said, yeah, there's something going on here, but it probably, and it was consistent with a certain color of the insulation, which meant that the insulation compounds were a little different and it absorbed in the moisture, and all insulation absorbs moisture, okay? Some more than others, but they all absorb a certain amount of moisture in there. That moisture over time can affect readings. Okay, so always things to think about. You get better results with XLPE XHHW-2 in a submerged, long-term, prolonged submerged location in raceways underground than you might get with a THHN THWN-2. Why? Because the test that gets done on the thermoplastics is only up to 21 days. So nobody really does long-term tests on this. Whereas we know that cross-linked polyethylene or XHHW-2, RHH, RHW-2, those type of products, even PV, all of those, USC-2 is a thermoset, all of those, even though they're not tested for extremely long term, their dielectric absorption rate is different than a thermoplastic material. Okay, so it doesn't absorb moisture at the same rate. So you have a better chance of getting a reading. Plus, it's a little more robust of an insulation. So you just got to know where you're installing it, what condition it's in, okay? But just remember, the path for return for these meters to work accurately, to be able to really understand these readings, have to have a return path. You have to have it. And if everything is insulated, where's your path? So with motors, it's perfectly fine because you have a primary, you have a winding, transformers, you have primary, secondary winding, there's separation. You can test the validity of the separation material with a Megohm meter. If it's the insulation or the separation resin is bad, then you'll get the reading. Okay, you'll get a reading because again, it allows it to push a certain amount of voltage in, and through the medium, you'll get a return value for current. Very small amounts of current, but that's all this meter needs in order to do a calculation for this, okay, and give you a value. Again, so the moral of the story here is, it's not a perfect science when it comes to wiring cable. It might be for motors, it might be for transformers, it might be for other things that have a separation material between two different mediums. But when it comes to wiring cable, if I don't have a good return path, I can't get really reliable readings. Now, I think what happens is we see a high reading, we don't care, it's high, it's above 100 megohms, and we just go, we're done. But I guarantee you, you come back and test it 10 minutes later, you'll get a different reading. Depending on the temperature, depending on the humidity, depending on the moisture, the values will change. Don't expect every conductor to be the same value, okay? It's never the same value when we make it at the facility, and it's certainly not going to be when you test it in an open air condition out in the field. Different values. Okay. All right. So we have some questions that came in from the people that are over in the video. So we'll kind of look at and see if we can answer some of the questions. And let's see here. Let me kind of come back and say, Ronbo, which is a follower over on our video channel, says, I would take it that the test is done prior to installation, or every time somebody posts it, it jumps. Or does it still being around the spool mess up any readings? I've done the 1 minute test once and it was pulled in. All right, so we put it on the reel and it's dunked. Being on the reel is not going to affect it. Okay? It's not going to affect it at all. Whether it's on the reel, again, so testing prior or testing when it's installed. Okay? Now, the only difference is if you test it after you installed, then you have the propensity for damage during the install. Okay? Right? So, again, I always recommend if it comes and there's a problem with how it's transferred from the truck that brings it to the site, I'm mainly going to do my continuity tests on it. I'm going to look for that seal that says it's been tested, that it's okay. Give it a visual examination. Don't see any evidence of any damage anywhere. I'm probably going to do my continuity on it, and it'd be the same if it was a cable. And I'm probably, since I'm not going to dunk it there, I am probably going to install it. And then I'm going to do my test if the job requires me to do a test. Not all of them require me to do a test. All right. So again, it doesn't really matter. The only difference is if you do it on a reel, it's obviously hard to test in the scenario of what we're taught. A to B, B to C, A to C, all to ground. Again, okay? So meg testing is pretty difficult when it's still on a reel, okay? Because you got no dunking ability and you've only got two ends of the conductor, okay? So again, it's not going to hurt, but that's more when I do a continuity test. I kind of do the meg test once it's already in the raceway, okay? Let's see here. The next question is from Robbie. It says, how do you know what reading is good in respect to the type of conductor, cable, etc.? Do you have a contact the supplier every time? No. So as I said earlier, you might have missed, Robbie, if I'm doing the tests, and I would encourage you to go back and watch the rebroadcast of this because I gave an example of what you're going to get at a 30-second test value. Take a reading at 1 minute, take a reading at 5 minutes, and take a reading at 10 minutes because I always recommend a 10-minute test on each one, okay? And when you start to do the ratios, anything when you're doing the dielectric absorption ratio, anything that would be 1.0 or greater, I would accept it when it comes to wire and cable, okay? Anything that I get that's a 10-to-1 ratio test that's 1.0 or greater, I tend to accept it at that point for wire and cable, okay? Now, with that said, if I do the time resistance, all I'm looking for is to make sure that when I get to, I'm taking it at 30 seconds. When I get to the 60 seconds, at that point up to the 10 minutes, it does not drop below the value that we got at 60 seconds. Okay, so it continues its climb up. Okay, as far as meg reading values, I typically tell people that, look, anything that's 20 to 25 mega ohms and greater, I'm happy with. Okay, Nita doesn't say that, but that's what a wire and cable manufacturer is going to say because that is pretty high insulation values, and we're taking all the conditions into consideration with that. Okay, let's see here. What other questions? Let's see here. Nick, I think there is an industry standard. It's called a Nita. If I remember correctly, less than 2 mega ohms is no good, but I could be wrong. Yeah, so there isn't one that says less than 2 mega ohms. I wrote a document called 2 to 99. Anything less than 2, something's going on. Doesn't mean it's bad, but something's going on. It needs to be investigated, and you should always contact the manufacturer. Always. If your values come between 20 to 25 mega ohms and 100, you should reach out to the manufacturer for that and just ask them for guidance. And they'll be able to give you guidance. So I'm not saying you have to every time. You're probably not going to run into this every time. But if you do get it, remember, it's just many things that could cause this to happen. Humidity, temperature, moisture, retention, water between the interstices of the individual conductive material, mutual capacitance because you were charging 2 conductors and then the next one didn't get discharged before you tested it. All these type of things can contribute to it. But just because one is a gigaohm and the other one's only 50 mega ohms does not mean that this conductor at 50 mega ohms is bad. It's just not 1 gigaohm, okay? Don't judge it as all things being created equal because each conductor is made differently. Now, in your mind, you're thinking, look, it's all copper. It's all aluminum. It's all insulation. I should get the same freaking readings. You're not. You're just not, okay? Now, you get lucky in some cases, they're very consistent, but you can have them swing. Now, interesting that I should say before answering more questions, we want to go over and look and see what the manufacturer shows. As an example, this is one of the manufacturers, shows how you would test a cable. And I found this pretty interesting. So if we go over and look at it, and I will go down to it and show you an example. And this is, again, you know, some of these manufacturers have really good documents. Okay, but I'm going to go down and show if I can, if they have it, if I can remember where here we go. So here's how it shows the different product testing. Okay. And again, showing things like control signaling of communication cables, and then it shows a power cable. Now, even in their own document, they show that the actual outer sheathing is lead sheathing. Of course, that could be EMT tubing, that could be rigid or whatever. Notice it's not non-metallic. So in order to get a good reading, you'll notice that you test one conductor under test, and you take the 3 other cables, okay, and you connect them to the sheathing that's metal. Why? Because anything that would leak here comes back on a return path, okay? Now we're testing this conductor, again, mutual damage, but we're also testing it to see that any insulation, the current that might be leaking out of it due to the voltage that's pressed into it, that we might get some kind of return path to this tester, okay? So even they talk about having a conductive outer core, okay? That's kind of sounds like an oxymoron. A conductive outer sheathing, not the core, okay? So again, this is by their own document, all right? Now, so this is just, again, not calling any individual, any company out. I'm just saying that's what they recommend, all right? So with that said, you cannot, if you can't get a return path, I can't. Now, they work really good on motors. They work really good on certain pieces of equipment that have a separator that has to be tested between 2 positions, whether it's grounded components and ungrounded components. Really great, okay? Does fine. But when it comes to conductors, it's not so much. I'll give you an example. I also had to do a test on NMB, and NMB has a bear in it. Okay, you with me? And what I wanted to do is I wanted to put enough current through a conductor that was insulated, that was damaged, exposing the copper. And I wanted to see what it would take to create an arc from the insulated conductor over to the bare conductor in the middle of NMB. Now, only thing separating is paper, right? Guess what? It took me about 5,000 volts in order to get it to bridge across that paper and spark so that I could measure it. So creating this takes a lot of voltage. So to simply think that I could put 500 volts or even 1,000 volts into an insulated conductor and have it leakage from one insulated conductor to the next insulated conductor, absorbed through that insulation in the mutual conductor that's parallel with it, and then come back to the meter, is that really something that you think can really, really happen? Unless there's mutual damage at a mutual location inside that raceway or in a cable, then you might get something. And then you probably recommend at that point to go to a high pot test so that you can complete that application. So if it is damaged, then it ends up burning it up in between them, and it's a destructive test versus a non-destructive MEG test, okay? So there's different things. Reach out to the manufacturers. But again, common sense. If I'm putting conductors in the ground, schools are teaching them to test a probe in the earth, check a conductor, and then test it to the probe. And I'm thinking, do you really think that enough is going to leak out of the insulation, into the earth, all the way back, and into your probe? No. Okay? No. It's not really going to happen. Are you going to get a reading? Yeah. And I'm just saying, use a little common sense. Again, call the manufacturer and ask them, was their products designed to be tested on 600 volt rated wire? And ask them this question. Do me a favor. Flood them with the phone calls. Call them up and say, hey, I've got 4 insulated conductors in a PVC raceway. Will your megometer work properly? Will it give me the readings if all of the insulation is on every conductor? And just ask them. See what they'll tell you. Okay. Let's see. I have some. Let's see here. Any other questions? I'm going to catch up with these questions real quick. So Robbie says, so in those instances where it's harder to perform a MEG test because it's wrapping of non-metallic tubing, okay, or non-metallic tubing, then how can you be sure we're getting accurate readings? Well, Robbie? You can't be. You can't. You can't. So the importance is to remember that the manufacturer does testing, which is more reliable than you. Make sure that when it goes from the truck to the site, that you treat your wire with tender, loving care. Okay? You notice any damage on it, you inspect it, it gets tested before it gets sent to you. Majority of the problems that I see in this industry is wire that was damaged on the site. Whether it was reeled too far away from its entry point to the raceway, it drug it across the ground, or they didn't put bushings in, or they didn't put the tugger in right, or the pusher right, or the reels right, and they drug across the side of the box. I find that to be the biggest problem with damaging insulation. Okay? But even with that said, I have seen conductors that get pretty darn damaged that were thrown into, and I've seen this because you know where I work. I've seen wires thrown in a non-metallic raceway that was severely damaged. We've tested this, and you test it with the MEG reading, and it comes out fine. Why? Because the only one that's damaged, the others are not damaged. There was no way to get a return path on it. So how could you get a reliable reading? You did get a reading, and it was probably a reading that make you go, oh, I feel okay about it. Reality is, if everything's insulated, even that damaged conductor would probably run forever and not have a problem until it's flooded with water, and then it becomes a problem because then it starts attacking the exposed conductive material. Then you slowly over time create a hot spot, a point in the wire that becomes resistive, and then all of a sudden then you have a problem because the heat will start to build up because of the increased resistance, and over time things start to break down, but that's because it was damage, right? Different things to think about, okay? It's not a perfect world, but it's things that you do have to think about. Paul will need to answer that one. I'm sure he get to it. I think I just answered that one. Okay. Let's see. The readings would be very low, around 5 ohms, if there was metal-to-metal contact, right? I don't know about 5 ohms, okay? But the readings would be pretty darn low. But again, there could also be low readings due to mutual contact. But ohms is very, very low. Okay, that's almost close to where we get a ring out. So if you got something that was that bad, then chances are good old Sparky will probably walk in there, and I always did. I walked in there, if it was all metal raceways, because I had a chance to get a good reading, I always took my continuity tester and tested every conductor to the metal box or to the actual raceway. And if that sucker ringed out like continuity, then I would look at everybody and go, we got a problem. We got a problem because this shouldn't happen, okay? That's the old school test that means the most to me is a real reliable meter that has a really good continuity test on it that I can check that type of thing. Other than that, you're just, the MEG readings can go all over the place. It's okay to use the Nita standards as a threshold and make you feel good. And when you get them over 100 megohms, you go, good, let's install this bad boy. All I'm saying is, when you get something that's below 100 and you get it down to maybe 20 megohms, don't freak out yet. Don't start ripping crap out. Then reach to your manufacturer of the wire or cable and give them the story so that they can give you some insight. That's all I'm saying. Okay, just don't start ripping crap out. Okay, engineers famous for that. Oh, it's below 100, rip it out. First of all, I can probably sure they don't even know what it means. And they don't understand megging well enough to understand that how are you going to test insulated to insulated products? Okay, enough of that. I'm coming off that soapbox. All right, it doesn't mean there's no place for MEG testing, because there is, and I gave you the reasons why. Medium voltage is beautiful. High voltage, it's beautiful. Motors, transformers, anything where you have a dielectric separation between ungrounded and grounded parts, then it can be beneficial in equipment, okay? But when it comes to the validity of insulation on a conductor, which can be pretty darn thick in mils, it's pretty tough if you don't have a return path, okay? Now, if I see a raceway that's damaged, crushed, cable that's been bent too much where it's caused the back end to pop out and you haven't followed the maintained bending radius, I'm going to test those, but it's going to be conductor to conductor. That's what I'm going to be looking for damaged, punctured insulation. That's what I'm going to be looking for. And then you might get a reading on that armor because it might have penetrated the polymeric material in an MC and it's poking into the conductive material. Then you might get a reading. Different things you can do, okay? Just know that you have people out there who are experts at this that can help. But people ask me, if I did a meg test on a raceway and I got 20 megohms, am I ripping it out? Absolutely not. I will investigate it, see what's going on, look at the condition. Remember also, when the temperatures change, you have to do a temperature adjustment as well because the values can change depending on the temperature that you're baselining, okay? So all these things have to be taken into consideration, okay? That's all we're saying with meg testing. It's not a perfect science. And again, I just ask you common sense. If everything is insulated, non-conductive, how are you getting a reliable reading? Are we really thinking that a weak insulation in the black conductor causes this voltage to be applied, the current to leak out, but right next to it, we have a red conductor that is also mutually weak that can pull it back? Now, all insulation is porous. We get it. Some more than others. But the whole body of an insulator is to insulative conductive parts. So you might get some readings. But again, it's really hard to get it to have current leak out of one, which is being applied the pressure by voltage, and get absorbed or pulled into a mutual conductor that's being tested. It's very difficult to do that. That's why you need some kind of conductive medium, like a metal raceway, okay, to be able to have that return path. Now, you could have a cable assembly with a bare equipment ground in there. There you go. You have a return ability inside of that to be able to do that, okay? Might be, but it has to be in contact with the conductors. Again, the NMB that I told you, it has paper separator. It really took quite a bit in order to be able to bridge any damage across to that bare conductor. It took a lot to do that. Not something that a normal meg's going to be able to deliver, okay? Let's see here. Ask a couple more questions before we end it here tonight, for at least for the people over in the podcast. Let's see here. Oh, distance, yes. Distance can also play a huge role on meg readings. Obviously, the longer it is, the more exposure of insulation you have to the actual test, okay? So again, the longer it is, though, the values start to drop. Let's see. Electricity is a wicked woman. Lightning will show you things you wouldn't believe. Least path of resistance is a fact. Okay, true, Thomas, but remember that when we're talking about things like equipment, and I'm sure you know this, equipment grounding conductors, things like that, electricity doesn't take the path of least resistance. It takes all available paths that are proportional to the resistance or impedance of that path. So it'll take all paths, not just the one with least resistance. It will do it proportionally, and the amount of current will be higher on the one with the lower resistance, but it's still going to take the one with the higher resistance as well. It's just proportional, okay? But yeah, it takes all paths. But you're absolutely right. Electricity is a wicked woman, and again, that's why bonding and grounding is so important. That's why I encourage all of you to attend my webinar on June 20th. You can sign up for it by going to our website, masterthenec.com. It does cost you $69.95, but it's 3 hours of it, and I explain everything about grounding electrode systems and the different types of electrodes and how they intermingle, and even other questions on grounding and bonding that you might have during that webinar, okay? So make sure you sign up for that. Limited seating. Visit our website for that. Let's see where else here. Were you on the same two panels for 2020? Yes, I was on Code Making Panel 5 and Code Making Panel 17. So yes. Let's see. What else we have here? Does Encore treat the paper NMB, or is it just the paper? No, all of the paper inside of it has to be treated. It's a fire retardant paper. Okay, it's impregnated, I like to say, but most people say it's permeated. I like to say it's impregnated, but you know what? You have a paper woman. Oh, anyway, you know what I'm talking about. Let's see, what's next? What does a high-pot test accomplish? Okay, well, a high-pot test is looking for insulation damage. And it's looking for any damage where it might take, remember what I said, what it would take in order to get the voltage to jump from an insulated conductor over to a bare conductor in an NMB? That would be more conducive to a high-pot test. Okay, because the voltages had to be so much higher. So in a high pot test, the voltages are much higher. It's usually going to take whatever the rating voltage is that you've got. It's that times 2 plus 1,000. Okay, so if it's 600 volt rated insulation, it'd be 600 times 2 plus 1,000. So we typically would be 2,200 volts, as that's what we would put in there for a high pot test. Again, the higher the voltage, the higher the rating. Those different things can change, and the manufacturers of the testers can give you the recommended values. But again, that's a typical rule of thumb that we use. 2 times the rated voltage plus 1,000 volts. It's typically what you do for a high pot. Not what you would do for Meg. Meg is usually 500 or 1,000 volts, okay, maximum, okay? And the other thing about it is, with a high pot test, that's it. It's destructive. It's either a pass or fail. That's it. Meg test, you're getting a reading, and it's non-destructive. With a high pot test, if there's something wrong or there's some damage, it is it. It's gone. You with me? It's a pass or fail for that. Let me catch up here. I got to go through some other tests. Hey, Paul. Hey, everybody. Also, thank you all for coming over to the video. Those on the podcast, consider joining us over on the video stream. That is at youtube.com/master the NEC. We would love to see you there. I did submit quite a few for 2020. I'm not going to really go into those tonight, but I did submit quite a few, and I've got quite a few submitted for 2023 as well. Okay. Let's see here. Yes, high pot is a pass-fail. Megger will give you resistant values. Absolutely. Now, they also make a tester called an insulation tester. And the manufacturers are kind of pushing that over Megger because, again, it's kind of focused towards insulation, but it's pretty much the same principle. I just remember, don't get fooled by the smoke and mirrors. Ask your Meg tester provider, say, if I've got a PVC raceway and I've got 4 insulated conductors in there, will I get reliable readings if I go A to B, B to C, A to C, and all to ground? If everything is insulated, and give me an email and tell me what they said. Call any of them. I'd be interested to hear what they say to you. Okay? All right. Anyway, that's it for tonight, folks. I will hang around and answer some questions on the videos feed over on YouTube. For those over on our podcast, thank you for listening on our podcast. Remember, we do this every Saturday night at 8 p.m. Central Standard Time. If you're trying to learn the National Electrical Code during the week, we have exam prep. Usually it's Wednesday nights at about 7 to 7:30. Feel free to join us over on our YouTube channel. That is youtube.com/master the NEC. Again, at the end of the day, if I offended anybody or you disagree with my position on this, send me an email. Prove me wrong. I love to learn. So tell me where I'm off on it. Explain to me where the common sense doesn't work right. Anyway, for those on the podcast, take care, and we'll see you next time. You've been listening to Electrician Live with your host, Paul Abernathy. All right, everybody. So we're done with the podcast, and we're going to have a little bit of time here for the video stream. I want to make sure I answer any additional questions that you might have. And answer anything that you want to bring to me that has to do with Meg testing or anything like that. Again, what I try to explain to people is that it's no certain science. And the manufacturers do the best that you can do under the controlled conditions. So when you get the wire, unless there's something dubious going on, when you get the wire, it has been tested, whether it's a dunk test or a spark test. Okay. And I'm going to tell you what, when you run those wire through those beads, the thermoplastics, and you could still dunk that if you wanted. When you run that through those beads, dude, it's putting anywhere between 3,000 volts all the way up to as much as 15,000 volts, depending on the size of the wire. Obviously, because the insulation gets thicker as the wire gets bigger, so the voltage gets increased. And those machines are designed to kick that thing off. That wire is done, okay? And for a manufacturer, it usually is going to go back to scrap, okay? So the only difference is if it ran 550 feet and then it arced because of damage, then it identifies where that is, and then they might be able to salvage a 500-foot roll of something because they'll identify where the damage was, and then they'll remove that, and it goes back into recycling, okay? But most of the time, what I see is they just say, screw it, and they scrap it and start over again. And so no manufacturer wants that kind of wire going out there. It's their reputation. Accidents happen. Things happen. We can't control everything. Again, there is a human element in everything, and it's sad it happens. But there's a lot of checks and balances that are in place. And so, again, it doesn't matter who the manufacturer is. Everybody makes a mistake. Things can happen. But typically, when the wire gets put on a reel and everything, you can be pretty reliable about it. There's a number of feet that are installed per year and in the millions and billions of feet. And you might have an incident here and there, but it's very rare, okay? Do your due diligence. Just remember that meg readings, even if they're lower than 100 megohms, does not mean that it is bad insulation. That's the key here, all right? Just reach out to your manufacturer. They'll help you. Let's see here. Let's see here. Paul, buddy, help me. Paul, you helped me a good deal, and I appreciate it. You're welcome, Sam. What would consider the 3 most useful testing equipment? Well, for me, I would probably say 1, a really good multimeter. And you're going to probably laugh, but I have used, and I don't use manufacturers' brands. They don't sponsor me. I have used all of the big names, right? I've used all of the big names, and you're going to find this pretty hard to believe, and I don't think I even have it here anymore. I'm pretty sure I don't. I actually invested in, y'all will laugh at me. Yeah, I don't have it in here anymore. I actually invested, and I got my ones that begin with an F, big well-known name. I actually have one from Harbor Freight that I use now, and a lot of the testing that I do, even in our facility, but even out in some of the projects that I still do. And I'm called out to do a lot of testing when people can't figure something out. That's all I really like to do anymore. I don't do big jobs anymore. I do small stuff, but if somebody's really don't realize something's going on or they're having trouble, they'll call me. I've developed that name, same as I had in Virginia as I came out here. So McKinney, Texas, or somebody calls me out, or Dallas, said, Paul, we're having trouble figuring something out, troubleshooting it. Do you mind coming out? Sure. And I use this meter, and it's actually one that I did a review on my website. It is basically from Harbor Freight. It's their top of the line one, but it is just really good. So a good multimeter is a must, okay? A must for that first one, okay? Now, the second most important tool, again, it's not so much a testing tool because I don't really believe you have to have so many testing tools. When I was in business, I had a meg tester, and I did meg. But at the end of the day, probably not my primary tool. I can be honest with you. I'm going to be totally honest with you. Back in the day, we probably only megged probably 5% or 10% of all the wires we installed. Now, I always did a continuity test between if it was paralleled, we call it in the industry paralleled when it's on one reel, black, red, blue. That's not really paralleling. You know what I mean. Paralleling would be 3 blacks, 3 blues, 3 red. But in the industry in cable, wire and cable, we call paralleling when you put a black, red, blue and you plex it and put it on a single reel. Okay? And yeah, you could joke about horrible freight. Call it horrible freight. Not me, buddy. I like some of the stuff I get from Harbor Freight. And you got to remember what you're getting. I've had it broken a tool and went back in there and they gave me a brand new one for nothing. Just said, there you go, take another one. But I will tell you, these meters are made for another company and they're branded. They're not made by Harbor Freight, okay? But they're made for Harbor Freights, but they're actually branded for use, okay? And they are high cat. Okay, they're fine for dealing, and mine's 1,000 volt rated, and it has a built-in ticker. And go watch that video review I did on it over on my channel, dude. I can actually map the wire in the wall with it. That's how sensitive the ticker that's built into the end. So it's a ticker, it's a clamp-on meter. So anyway, I didn't answer my question. So I don't necessarily say you have to run out and buy a Megger. If you have a big company, you have a company that does a lot of testing, definitely have your voltmeters, a really good one, whatever you feel comfortable with. If you don't like Harbor Freight, go with whatever you want, but get a decent one you feel comfortable with. A good Megger. I'm not going to tell you the brand. All of them about the same. The brand that begins with an M, it's not so bad. And again, I also, one of the things that I had was I did not have the IR cameras. I had the IR gun for measuring temperatures. And as a base rule, I used that on various terminals and things like that to get readings. And that was my 3 most reliable tools. But I didn't always use the megometer. But I always use my voltage meter. I always use my IR gun, just a simple IR gun to measure terminals, different contact points, motor temperatures, things like that. Back in the day. Today, if I was doing it, probably could get a nice one of those imagers that tell me temperatures and things like that. Maybe. But you say 3 things. I think you need a good tester, and you need a good IR gun, okay, to measure terminals, because you can always tell if a bus is overheating because it's a loose connection, things like that. Those are more, and of course, a good drill, good tools. But other than that, testing equipment, I don't know. If you're a company that can afford a megometer, then get a nice one. You don't have to get the $30,000 ones, okay? Remember, you're dealing with usually 1,000 volts or less, so you only need to gear towards that kind if you want. Not bad to have, but you only need it if you're going to be doing meg testing, okay? Megohms meter testing. Other than that, good voltmeter. And I always say a ticker, but I don't rely on tickers. I test everything. I don't trust those. Now, I like the one that's on the Harbor Freight one that I have, because again, you can map in the wall with it, and it's very reliable. And you can bet I put it through a lot of tests, playing around with stuff. Okay. Anyway, I don't know if I gave you 3, but that's the best that I do. Now, if I was doing maintenance, I definitely would have a thermal gun. I would definitely have a good multimeter. Definitely. Maintenance testing. Let's see. Ramiro says, what is the minimum cover requirements for swimming pool? What do you mean minimum cover requirement for swimming pools? Not even sure what you're talking about, that minimum cover. You have 680.26 equipotential bonding. You have the bonding shell. You have the perimeter. You have all metal parts within 5 feet, all that type of thing. So I don't know what you're talking about, but I don't know that has anything to do with meg testing tonight. Robbie, so HiPod tester is essentially the best test to check insulation. No, Megger's the best for insulation. Okay? That would be the best. When we go to a HiPod, that's when we think that there's potential damage to the conductors and I need a higher value. So I might migrate from a meg test up to a HiPod test. If I get really low meg readings, then I might bring out the HiPod, because what I'm going to do is use a much higher voltage, and it might take damage and then blow through that damage, and then you'll get a pass or fail. And then you know without a doubt that it's got to come out. Okay? Let's see. There you go, Cat 4. Yep. So even the one from Harbor Freight, I believe, is, and I can't remember the Cat class, but I know that it's 1,000 volts or less. I don't do anything with utilities, so I don't worry about that. All right. Well, that's it tonight, folks. We're going to leave up tonight. We're not doing exam prep tonight. Ramiro, if you have a more specific question on swimming pools, you can email me at info@masterthenec.com. I'm more than happy to try to answer your question for you. But that's going to be it tonight. So hopefully you got something out of that, folks. Until next time, stay safe. God bless. You've been listening to Electrician Live with your host, Paul